this is very simple, and somebody was asking about the book. I think you can follow Art Shankar, or there is a book which I don't know, old book I followed, which is called Anderson. Let me write quantum mechanics or modern physics by Anderson. But I generally don't follow books nowadays. I just from my knowledge I write and kind of thing. So I maybe mismatch, and also lot of books in my office. It is lying, and I'm taking classes from home. But Art Shankar book, Anderson book, Griffiths book, these books, any notation, they only differ by notation, idea, etc. Everything is exactly same. So there will not be any difficulties. So do you have any question regarding this two? If it is clear, then I will move ahead to find the second order correction to the energy level. So En2, this we are going to find. Okay. So for that we use that equation, that three equation we wrote by comparing the lambda from both sides. These three equation, you remember 3, 7 and 8 in last note. So these two equation I have used, equation 7 I have used this.
Sir,
Huh.
sir, is was there any reason that we only expanded the Hamiltonian up to one, but the energy eigenvalue up to two places when we were writing this equation?
No, this is for simplicity. See, we want that what will be the energy eigenvalues. So energy eigenvalues by our assumption, it is like this. Equation 5, if you can see. So this is
Yes.
like this. So we'll go by calculating this term we already know. Then we calculate this term. Then we calculate this term. This is the idea. And this term contribution is most because lambda is very, very less than 1. So this is greater than, so lambda E n1 is much greater than lambda square E n2. So we get a major correction, then little bit lesser correction, then less and less. So in principle, if you can, you have to find this infinite series, but this is impossible to do. When we do approximate things, we need to get only first or second terms, and that will give, sometimes that will give you very accurate result, not exact but accurate result. Okay. So this is for simplicity. Answer to your question is for
Okay,
for
sir.
yeah, we cannot do all order calculation. See, you can see that second order will be difficult, much more lengthy, third order will be much, but in
Sir,
computer,
but
if
we
you
are
write a
only Sir, but
huh,
we're only doing for the Hamiltonian, we're only taking one extra term. Why not two?
Hamiltonian, where you said Hamiltonian, we have only one term.
So
This term,
here, yes, sir, we're only taking lambda h prime, but not
this is
lambda
H
square h prime.
prime. This is not H1. This is H prime.
Okay, sir. So it will not.
This is no. This is the whole Hamiltonian. This is the full Hamiltonian.
Okay, sir.
This is full. There is no approximation here. I use a lambda here to make sure that this term has to be smaller compared to this term. Otherwise, this method will not be valid.
Okay, sir.
So this is
Okay.
a full Hamiltonian. This equation 1 is full Hamiltonian, and that is
Okay, sir.
prime.
Thank you.
So please make difference of prime and 1, 2, 3. Energy levels I wrote 1, 2, 3. An eigenfunction I wrote 1, 2, 3 for first order, second order, third order, even 0, 0, 1, 2, 3. Zeroth order correction means there is no perturbation, no interaction. Okay. And H prime is my additional term, full term. Okay. Okay, so now the second, let us take this equation that, uh, or maybe here itself I can erase and do, because I don't need to write. So this lambda square equation, let us concentrate on lambda square equation. Okay. Okay, so this lambda square equation, now I need to calculate this quantity, okay. So I take a inner product with n0 bra n0, n0 I am writing the labels, I should write in the upper position. So n0 and multiply this equation this. So what will happen? First term will be h0 n2, second term will be n0 h prime n prime. Okay, the right hand side, this is constant, so e n0 will come out, n0 n2. Okay, second term on the right hand side will be e n1 also will come out, n0 n1, and last term will be en2. Okay. So first step we did, we just because this term we have to calculate, so that give our hint with whom I will take a inner product. So I just take a inner product with n0 in equation 8 to get this equation. Now first thing I'll show that this term and this term are equal and they will cancel from both sides. How I'll show that? This is H0. H0 is a Hermitian operator, so it can act on bra space. Also, it can act on the Ket space. This is Ket, this is bra. So when H0 acts on the bra space, it will give you a E0, En0, and then N0, N2 term. So which exactly same as this term. So this term cancel with this term. Okay. Is that clear? So argument is H0 is a Hermitian operator. Hermitian operator can act on the Ket space as well as bra space, because when you go from bra space to Ket space or Ket space to bra space, you will have to take a Hermitian conjugate. Okay. So that is why so this term and this term get cancelled. So I can write from my En2 is this term n0 h prime n1 and then e n prime n0 n prime. Okay. Now I already know that I can write my n n1, this is not prime, n1 that we already calculate. N1, if you remember, it was sum m which is not equal to n c n m and m0, right? This is hello.
Sir, it should be minus en1 now.
Yeah, you are right. Good. So this will be minus. You are right. But anyhow, this is going to 0. Anyhow, so this should be minus. I take it from left side to right side, so it should be side change, so minus sign. Good. Okay. So now if I substitute this n in that second term in the right hand side, this term, in both the terms. In fact, I will substitute it in both the terms. So what will happen? So let me write En2, second order correction to the energy. So this term will be N0. Then there is a H prime operator, and then you have sum over M, C N M, and this will be M0. Just a moment. This okay. Let me write. I don't know whether this will be helpful or not. But second term, I can simplify En1 and then N0. Remember this M sum over all possible values except N. That I argue last time. So this was sum over C M N, sum over M which not equal to N, then M0. Now this term only survive where m equal to n, because n0 inner product will be 1, n0 is 1, and any other combination will be 0 to orthogonality, and this term has all the term except n, so this term is 0. That means n0 m0 is 0 when n not equal to m, because of orthogonality. Yes, Tripathi.
No, sir,
Yeah.
गलती से
Okay, okay. So this is that and term, and now we are going to substitute your this term will not substitute, will not helpful. So let it be. This term I'll cancel. Yeah, I'll substitute something else. I'll tell you immediately. This is n prime, n1. n1. Okay, so I had n2 two terms. The last term which minus sign is 0 because this argument. Okay, good. So now this term we have to calculate. We are almost this is the second order correction, but we'll write this term in little bit familiar way, and today we'll consider one example to how to calculate these three quantities. Already some students showed me that they can calculate for the perturbation x, which I asked you to calculate. Okay, good. Now this n1 first order correction to the eigenfunction we already calculate, right? Remember where we calculate that second formula. Oh, probably I have erased, or let me show in the down. Yeah, this one. So this we calculate yesterday. So we'll be using this to that. So let us put that. So this is now your n0, then h prime. Then I'll write my n1. N1 is sum over. So let me write sum over m not equal to n. Then what are the things? Then m0 h prime n0, then m0 h prime n0, and then there is a state m0, right? m0 and this denominator m0, and then denominator, let me check, en minus em. Okay, en0 minus en0. So this I just substitute n1, which I calculated yesterday in this. Now this I will write in a little bit nice formula. This summation I take outside. Let us take this summation outside, m, which is all values but not n. Then I had n0 h prime. This is the inner product, this quantity inner product, so number. So I will bring this state here to m0, and this is your m0 h prime n0, and the denominator n0 minus n0. Okay, this is my E2 En2. This can be further simplified, and then see this quantity and this quantity, they are same or different. Let me ask Nilesh Bharti. I can see you in front of my eyes. Nilesh Bharti.
Yes, sir.
Can you tell these two quantity are same or different or what?
Sir, these should be same.
They are same. Just look at carefully. This is n0 h prime m0. This is m0 h prime n0.
They are different, but their calculation should be same because H is Hamiltonian.
H is Hamiltonian, but there the states are, see, first day I wrote when I xp is not same as px, no? This inner product with x,
Yes, sir.
it's complex conjugate. You remember? This should be complex conjugate. When you change bracket, it will be complex conjugate. So this term and this term are same, but they are complex conjugate to each other. So I can write. So when you have a term like this, z star, that means mod z square. So this is, suppose this is z, then this is z star. Okay. So this I can write. This I can write sum m not equal to n0 h prime m0 mod square, but e n0 minus e0. Here you can change, interchange n0 m0, you can interchange because mod square is there. Okay. So this is your final formula for nth order correction to Ravindra Gorai. You raise your hand. Tell me. Tell me. I cannot hear.
Hello.
Your voice is breaking. Tell me. Hello. बेटा सुनाई नहीं दे रहा है. I'm just waiting. इस क्लास का टाइम बर्बाद हो रहा है. तुम अगर ऑडियो ठीक नहीं है कि तुम्हारा इंटरनेट पुअर है तो you ask me later, or if you want you can write the queries in the chat box also. I'll try to say. Okay, so 3 formula we obtained, and that's all. These 3 formula for any competitive exam, this is all. So first is n0 h prime n0, this, then e2 is already written, this is your e2, and then e1 prime was m0 sum over m not equal to n cm. No, there is no cm here, cm already substituted. M0, then h prime n0, then e n0 minus e m0, and then m0. Okay, so let me check whether I did mistake or not. Yeah, this is the, so m0 h prime n0 e n e m0 m0. Okay, let me clean little bit. Okay, so this is my 3 formula. If you know these 3 formula, you can solve any problem in perturbation theory, non-degenerate perturbation theory. Okay, that I'll tell you. So I'll give you a lot of problems. So if you practice, you will be master in doing solving. So 3 formula. What are the 3 formula? First order correction to energy, second order correction to the energy, and first order correction to the eigenstate. Of course, these 2 are infinite series in general. So you have to be careful when you find the answer. You generally need to find, when the question is asked, generally ask that first find first 2 terms, or here if you are infinite series, you have to find first few terms, kind of thing. But this 3 formula, now you can solve any problem. So let us consider some examples. Okay. Yeah, ask Sahu.
Sir, second order correction in the state vector is not necessary for you?
No, see, the first order correction to the state vector is the infinite term. Okay, so second order correction is of course necessary. If it is necessary, then you have to calculate. I mean, these are the bare minimum. We are not calculating second order. Yeah, it is necessary. It is necessary, but you cannot calculate analytically all these things, and first you learn to calculate these things. So let us understand these three formula. If we can understand these three formula, then it is good. And I'll today I'll consider the example I considered last time. Let me make it in a formal way. So that is a very nice example. So all of you are familiar with operator method of harmonic oscillator.
Yes, sir.
Operator creation annihilation operator method. Uh, those I may assume that few student may not know operator method. Then please learn it from your friends or from Griffith's book or any other book because that is very essential for and because of lack of time we cannot cover. So let us consider a problem. Suppose a charge particle, a charge harmonic oscillator, charge simple harmonic oscillator. Charge means it has charge, say q, okay, q, charge, mass m, harmonic oscillator, angular frequency omega, and it's a magnetic field, electric field, in the electric field. Okay, so you have to find energy eigenvalues, eigenfunction of a charge harmonic oscillator in the electric field. Say let us write E in around E0x. I am making simply electric field is constant and in the x direction. Okay, x direction because now we'll consider one dimensional. So only x direction is there, and along that direction there is the electric field. So you have to find eigenvalues, eigenfunction, and in that finding you need a help of perturbation theory. Okay, so first thing that you have to write your Hamiltonian. Okay, H0 plus H prime. Okay. Okay. So lambda I am not writing, but lambda is just to show that how it works. Okay. If you make sure that H prime is smaller, I can assume that my electric field is small electric field. So this problem you can solve only on the small electric field. So there is no need of lambda. Okay. Otherwise, if you are not sure, then you have to make sure by putting a lambda, and at the end you can take lambda equal to 1 to get the result, no problem. So lambda is some role played by the intermediate roles. Okay. Okay. So first thing you have to find the Hamiltonian. H0, I think H0 is known to you. For example, if I ask Ranjit Behra, what will be the H0 for a harmonic oscillator?
Yes, sir.
H0.
Sir, p square by 2m plus half m omega square x square.
Half m, good, omega square x square. This is a harmonic oscillator. So that, and we know that H0 n acting on that E n0 of n0. This is known to you, right? Everybody knows that E n0 is n plus half h cut omega. So this is the unperturbed. This is the H0 is called unperturbed Hamiltonian, and unperturbed Hamiltonian is known to you, and wave function is known to you. That in terms of Hermite polynomial e to the power alpha square x square hn alpha x type of right. But remember, this 0 is the zeroth order correction, that 0. It is not the ground state. So don't confuse ground state. When n equal to 0, that will be the ground state. Okay. So n is 0, 1, 2 to infinity. So this is H0, and you know the solution. Good. Now tell me somebody else. What will be my H prime? If there is a charge particle in the electric field, what will be the Hamiltonian for a charge particle in the electric field? Anybody from BHU students?
सर एक टर्म और ऐड हो जाएगा
हाँ, that is fine. That is
Q into electric field into X.
so how you know that how to Hamiltonian is energy, right? So when you have a charged particle in the electric field, you will have Pokhar Singh. Tell me, Pokhar Singh, what will be H prime?
Sir, minus Q F naught X.
Yeah, how you get this? Just remembering,
Sir,
or
we have to add some potential energy, and in electric field, force is minus Q into E mainly. Electric field.
Okay, so this
Then,
is basically the work done, right? So work done will
yes,
be
sir.
the energy cost means the work done, right? So it will be E dot ds. So if you integrate 0 to x, so it will be E q0 x. Okay, so this will be your H prime. Where will be the potential energy? Somebody said potential. There is no potential, other potential. This is one dimensional. Potential energy is this. This is the potential energy of the harmonic oscillator, and this is coming from the electric field interaction with this. So my Hamiltonian now H prime is minus Q E0 x. But we don't know how to solve Schrodinger equation corresponding. We know the solution of H0, but we don't know the solution of H, and it can be. So how it can be done? Tell me. There are many ways, but one is the perturbation, because I am going to show you the how to use the perturbation technique. And is there any other way to calculate? Okay, we'll
So
do
we can
both.
complete the square.
Who is speaking?
Sir Sonal.
Okay, BHU or?
No, sir. Not
se?
BHM. Sir, Delhi University.
Which college?
Rajdhani College.
Oh, it's great college. Okay, you can do the perfect squaring. Then what will happen?
So we'll get an additional term, and the nodes will change, and also will the potential. There'll be a change in the potential as well as the lowest point in the potential and all the nodes.
Okay. Okay, so that we'll see. Okay, good. So that is the answer I was asking. Now my complete Hamiltonian is p square by 2m plus half m omega square x square minus q e0 x. And we don't know solution, but this problem of course can be solved exactly. So no need of perturbation, but still we'll do this, verify that our perturbation technique also give the correct result. So because we are first learning perturbation, so we'll consider some example which can be solved exactly. How? That Sonal said that, okay, you can write this as p square by 2m plus half m omega square, and if you take half m omega square common, then this will be x square, and this will be 2q e0 by m omega square x, right? Which I can write p square minus 2m plus half m omega square, half m omega square x square minus 2 into x times q e0 m omega square, plus I can write q e0 m omega square whole square minus q e0 m omega square whole square. I can do that. This term will cancel with this term, and this is the same term. But these three term is a square minus 2ab plus b square, right? So I can make a perfect square. Okay, I'm going very slow, so don't worry, but we'll go fast also. Some student Sonal will getting bored that she already knows this answer. Okay, so then this plus and there is a minus, so this minus I take outside, so minus I'll have I did correct half m omega square, then q square E0 square by m omega square whole square. So this m omega square, this will get cancelled. So this term will be, anybody ask any question? No. Okay, so this term let me write half q square E0 square m omega square. So now I have a new Hamiltonian, which is my again a oscillator. This is oscillator, but this oscillator is oscillating. So let me write. So this oscillator potential is half m omega square x square. That's oscillating about 0. This oscillator is oscillating about q e 0 m omega square point. This point is, so in this point it is oscillating. So this kind of oscillator is called shifted oscillator. So this is shifted, that it's that point around it oscillate is shifting to this point. But quantum mechanically energy eigenvalues, eigenfunction will be same apart from this shifting. Okay, but this oscillator new Hamiltonian is now a new H0 minus half q square E0 square m omega square. So what will be the energy eigenvalues of this oscillator? This shifted oscillator will be, energy eigenvalues will be En0 will be n plus half h cut omega and minus q square E0 square by 2 m omega square. So this will be my new energy levels. Okay, agree or not? If I have a Hamiltonian H prime or H equal to say H0 plus C, C is a constant. So if H0 has levels like this, then H will have level above C, C is positive, so we will have the more energy, C amount of energy more. So that is negative in this term, so we will have this term. So this is my new energy and eigenfunction. Eigenfunction, if you write in terms of your alpha square, now x square, now this x will be x minus q E0 m omega square. So x minus q E0 m omega square x square, this, and then h n Hermite polynomial alpha you just remember what is alpha, I forgot the value, times x. This x is x minus q E0 by m omega. So that will be now. So this problem can be solved exactly, and the energy eigenvalues we have found. Eigenfunction, don't bother, we will not verify eigenfunction. You those who are interested can verify. So now we'll do this problem by perturbation method, because now this is the energy, this is a correction to the energy eigenvalues, whether we can get the same correction by our perturbation method or not. Okay, so first thing, how the perturbation, so nth order first order correction to the nth level will be n0 h prime and n0. H prime is nothing but your minus q E0 x, E or E0 x. So this will be minus q E0 and n0 x n0. Okay, but this quantity I already argued last class that this quantity is 0. How? Because in harmonic oscillator all the state has a definite parity. Definite parity means either plus parity or minus parity. It cannot be a mixed parity. So suppose n has a even parity. So this is even under parity, this is even under parity, and this is odd. Parity means x going to minus x. Right now, so under x going to minus x, this is positive, this is positive, this is negative. So whole quantity will be negative, x going to minus x, and this is basically integration psi n star x x psi n x dx minus infinity to plus infinity. Now if this is an odd function, then this integration is 0. That is that. So this I argue last time. You try to find yourself this argument. Now if n has a negative, suppose this wave function has a negative parity, that means when x going to minus x, it will be minus. So this is a minus, this is a minus, and this is a minus. So 3 minus. So either it will have 1 minus, so that whole thing is negative, or it will have 3 minus, so whole thing is negative. And you know minus a to plus a fx dx equal to 0 if fx minus x is minus of fx, odd function. So odd function with the equal. So this is simple. But here I want to ask a question. How you know that a harmonic oscillator states have definite parity? That means either odd or even. That is the argument, depends on that, right? If it is a mixed parity, this is a mixed parity, then it will not be 0. Okay. So that how you know the simple harmonic oscillator have definite parity. Okay. Okay, so I'll give you the answer, but you have to prove yourself. Any Hamiltonian which commutes with the parity, then the eigenfunctions of H must have definite parity. Okay, so prove this. If harmonic oscillator H is parity, this means parity invariant. So if your Hamiltonian is parity invariant, then the wave functions will have definite. This is my harmonic oscillator. X going to minus x, p will going to minus p, x also going to minus p. But this is p square, this is x square. So nothing will change sign. So this part of the Hamiltonian is parity symmetric, or this part of the Hamiltonian commutator with p parity operator. So that is why definite parity. Okay, so this is your homework kind of thing. You just prove yourself. Good. Now, but our energy correction in direct method, we find there is a correction. But when we find the first order correction is 0. So what about second order correction then? So second order correction. So let us calculate the second order correction. Second order correction is En2, and this formula also we know, m not equal to n, and then we have what I had, n0 or m0, second order correction. I had n0, but that doesn't matter. N0. Then H prime is minus QE0 x, then M0, then this mod square, and then you have E N0 minus E M0. Okay. This I can write q square E0 square. So I take common. This is constant. You can go outside, and plus, and then we have this summation m not equal to n n0 x m0. But now they are different states. So I cannot say that they are this inner product will be 0. n and m will may have different parity. So these have different parity than this parity. So or this is mod square. So it can be even function. So it is not 0. E n0 minus E m0. Okay, so now let us calculate. To calculate this, we need that x. It will be easier for us. X can be written as Kiration annihilation operator. So if you remember, I don't remember, but let me see from my notes. Root over h by 2m omega, right? By
2m omega h cross.
2m omega. That's all, no? Then this a plus a dagger. Is that correct?
Yes, sir. Yes, sir.
Yes, sir.
Yeah, this is correct. So this a and a dagger I have to write. So let us substitute, because I know a acting on n is root n times n minus 1, and a dagger acting on n is root n plus 1, right? Root n plus 1 n plus 1. This how calculate. So without going to the integration calculation, I can calculate by using this formula. So let us calculate what is my n0 x m0, and we will write sum over m. Okay. So let us try to calculate, or maybe first let us calculate. So keep this factor outside again. This factor I will just write n0 a dagger times m0. Okay. I'll give. So my factor is outside factor is first q square h square, then this factor is also. So outside factor will be q square e0 square, then it will be h by 2m omega, right? The square, no? This x is inside the square, so it will. So this is the factor outside. Okay. Now let us calculate this. So what will be n0 a m0? So it will be root of m0 times n0 m0 minus 1, right? So it is root m0 delta n0 m0 minus 1. Similarly, n0, where a dagger m0 will give you root m0 plus 1 delta n0 m0 plus 1. Okay, so now for arbitrary n and m, it is very difficult to calculate. So let us fix that n. Suppose I want to check for where n0 is basically n equal to 1, n equal to 0, ground state. So let us find the ground state. So this term I have calculated this plus this. You know how you get this. This is from the orthogonality condition. When n0 and m0 minus 1 will be same, then it will be 1, otherwise 0. Where n0 and m0 will be same, then it will be 1, otherwise 0. Okay. So now you can calculate, suppose for ground state, correction to ground state. To get a for arbitrary n and m, this will be the answer. But now let us and you have to sum over all this. Sum over m is there. So correction to ground state. So what will happen to that? Now my n0 is n is 1, right? So n is 1, then m can be 2. Right? No, I want to ground state means n equal to 0. So n equal to 0. 0 is the ground state. N equal to 0. So n0 n0 will be 0 to the 0, 0th order 0, and then m has to be 1. So first term, this term will give you root 1 and this 1. Okay. Now second term. Second term is will survive n0 is 0. So if n0 is 0, second term always 0, will be always 0. Why? Because it will increase. I can have possible, m cannot be minus, no? M cannot be minus, only minus, then it will survive. So this is 0. So what is the whole term I get? N0 minus q E0 x m0 mod square E n0 minus E m0 hello, just a moment. I think my this has iPad has disconnected. Hello, can you hear me?
Yes,
sir.
Yes, sir.
Yeah, but you cannot see the screen, right?
yes, sir.
Yes, sir.
Sir, I
Yeah,
can
Yes, sir.
see.
some people can see, but I don't know. So so let me
No, sir, not visible.
stop sharing, and then again we'll start sharing. Uh, okay, broadcasting was start broadcasting. Okay, so yeah, so now let me go to my handphone.
Sir, I'm confused taking the values of n and m.
I'll remove your confusion. This, but let me get back to my screen. I think number of I have to pin again. Let me start sharing it. It's showing broadcasting, but sorry.
Sir, we can
You
see your
can
screen.
see, but this is funny. Then I cannot see why. Okay, so everybody can see my screen.
Yes, sir.
Yes, sir.
Yes, sir.
Yes, sir.
So tell me what I have written now.
A
A
plus
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 B.
B.
Plus B.
Okay,
Sir,
A
A
plus
plus
B.
B.
Okay,
A
good.
plus B.
I
Plus B.
cannot see
A
the
plus
screen in my laptop. I can. Okay, so let me today's meeting. I have 10 minutes, 7 minutes. I'll continue. Okay. See, m is a variable, right? You remember that second order correction. Second order correction n of the nth level, that is in our hand. Second order correction to ground state, second order correction to first state, first excited state, second order correction to second excited state, that is in our hand. So one can calculate n0 to, one can calculate n1 to, one can calculate n2 to, one can calculate. So this n value in your hand. If your arbitrary value n, I wrote n. Okay, m values is sum. It can be 0 to infinity, any values except n. So if it is zero values, in the n is zero values, m cannot be 0. If it is this state, then m cannot be 1, and that is the infinite series. So let me get this result before we stop. So in the first calculation, so this h cut by 2m omega square, no, only 1 2, no, both 2, okay. And then we had, so let us calculate only for the n equal to 0, okay. So n equal to 0 case we are calculating, so we will have n00 minus n. Now which value of m it was survived? Which value of m value of 1, right? M value of 1, it survived this term. This term never survived for the ground state. If it is a ground state correction, then m0 cannot be 0. M cannot be 0 because I am n equal to 0. M is not equal to n, so it cannot be 0. So m equal to 1, next possibility, and next possibility, it is creation operator. So one state will be converted to state, but it is only the ground state. Orthogonality will give you 0. So this term will vanish. So this term is there, and then you have E0 0 minus E 1 0. So is half h cut omega, and E 1 0 will be 3 by 2 h cut omega, right? So their difference will be minus h cut omega. So we will have minus q square E0 square h, why h cut square? I don't think it is h cut square, no? A dagger formula, it is root of h m omega, so it will be only h, and m omega, so it will be only omega. So root and mod square, so root will go away, okay. So this may make this correction. So after that we have to match the answer, whether we will get the answer or not. So 2m omega and then h cut omega. So this will get cancelled, okay. So answer that correction, second order correction to the ground state, E0 square 2m omega square. So this is the second order correction to the ground state. Okay. Now let us see exact solution. See, q0 square E0 square 2m omega square. So when n equal to 0, so you get that ground state minus this. So this is the correction. So I am getting this exact correction here. So now the student who is confused about that, you are getting m0 and n0, then
Yes,
for
sir. Yes,
you,
sir. Yes, sir. I am clear.
So for you, let us calculate, for you calculate the second order correction E1 2. This is the second order correction to n equal to 1 state. That means first excited state. Again you will get this value. In second excited state, second order correction, that means for n equal to 2, you will get again this value. Remember, when you do this, your m cannot be 1. When you do this, your m cannot be 2. This is because our formula, some m not equal to m. Okay. So this you do. I don't have time today, and also do this calculation, this first order correction to the eigenstate. And for this, let us take n equal to 0. So n equal to 0, taking n equal to 0, what you have to do? Which formula? The third formula. So this three formula we have derived. So this formula. Again now ground state correction, wave function, ground state wave function correction. So n equal to 0. So m cannot be 0. So other values it can be. So m can be 1, 2, 3, 4, provided this will be non-zero. So at least 2 terms or 3 terms you can calculate. So I'll tell you what to calculate. So it is sum m not equal to n, then you have n0 h prime m0 e n0 minus e m0 and then m0, right? Okay, so this you have to calculate. This is my first order correction to the energy. Now suppose n equal to 0, first value, ground state correction. So m cannot be 0, so this sum will be n not equal to 0, and this will be 0, first order 0 state, and then this will be root h by 2m omega times a dagger, and then this m0. Now m cannot be 0, so m can be 1, so you put 1, find the value. N can be 2, find the value. So calculate this n00 minus e m0. Okay, so calculate this term for m equal to 1, 2, 3. Very easy to calculate. Okay, so you calculate and you get the correction. So this correction will have some term with 1 0, some coefficient times 2 0, some coefficient times 3 0, and so on. So is that clear? Okay, we'll consider next class. Also, we'll consider some example, and by this time I'll try to give you some problem which you can do yourself. So maybe before your Saturday class, by Wednesday I'll try to give you some problem to calculate using these three formula. So once you are familiar with these three formula, then we'll go to that different theory, that perturbation, perturbation for degenerate case. Now we are assuming that all levels are different, there is no degeneracy. Okay, I'll stop here unless you have a question. Okay, so you have no question, so let me stop sharing. Stop recording first.